A student does a series of reactions with aqueous solutions of some potassium halides P, Q and R of equal concentration. So potassium halides are when we have K and then the halide ion, so K plus and the halide ion X minus. Each solution contains a different halide, so we've got chloride, bromide or iodide. The student adds 3 drops of bromine water to 3 drops of each of the halide ions, and the student also adds 3 drops of bromine water to 3 drops of water. So what do we see when we add it to P? We see an orange solution. Now the orange solution tells us we've got bromine, so we've added bromine to one of the halide ions and we've stayed as bromine. So whatever's happened there is not a reaction. The brown solution is iodine, so we've added bromine to our halide ion and we've ended up making iodine. That tells us that X minus must be iodide. Here we've got bromine, and when we add it to water, we're just diluting our bromine. Okay, so identify the halide ion present in Q. Well, the halide ion, and be careful, we do need to put the halide ion, so don't write iodine, it must be iodide, and write an ionic equation. So we're adding our bromine water to our iodide ions, and the reason we got a brown solution is because we made iodine. We're displacing, it's a redox reaction, so we'd get bromide ions. So we would need a 2 here and a 2 here to balance the equation. Explain in terms of oxidizing ability. So an oxidizing agent is an electron acceptor. So this is its ability to accept electrons. Why the observations from these reactions do not allow the student to identify the halide ion present in P and the halide ion present in Q. So how could we not be able to identify P and Q? So we know that we had bromine, chlorine, bromide ions, chloride ions and iodide ions. We've been able to identify iodide. But Br2 is not a strong enough oxidizing agent to oxidize Cl minus. Now Cl minus is smaller, so in terms of shells and shielding and attraction to the electrons, the Cl will have stronger attractions to the electrons. Br2 is not able to accept electrons from Cl minus. Okay, so we can't oxidize chloride ions, and Br2 isn't going to be able to oxidize bromide ions either. They have this, the same ability to attract those electrons. Br2 is not able to oxidize Br minus. It has the same oxidizing ability as itself, so it's not going to be able to do anything to itself. The student does a second experiment to determine the halide ions in each of P and R. The student adds a few drops of aqueous silver nitrate to 2 centimeters cubed of each of the halide solutions. With P we see a precipitate, with R we see a precipitate. What further tests can we do to identify the halide ion present in P and the halide ion present in R? So remember that we're left at the moment with Cl minus and Br minus, but we don't know which way round they are, we just know that we've got these two. So what is the further test that we could do? Well, what we know is that when we form, whichever one forms AgCl, the white precipitate, that white precipitate is soluble in dilute ammonia, whereas the cream precipitate AgBr is insoluble in dilute ammonia, but only soluble in concentrated ammonia. So the difference is to do with dilute ammonia. So we do need to be careful. We need to add dilute ammonia. The Precipitate AgCl formed from Cl- ions is soluble, so will dissolve to give a colourless solution. The precipitate AgBr formed from Br- ions is insoluble in dilute ammonia, so will remain, and that's how we could tell them apart.